Welcome to Lesson 14, Rates of Change in the Natural and Social Sciences. So this begins the place where we start to shift our focus. We've spent the last 8 lessons or so trying to focus on how to take a derivative, finding derivatives. And now from this lesson on, we're going to be looking for several lessons at what to do with derivatives, how we can apply them in different scenarios. So it's going to be looking at it as a rate of change and that kind of thing to learn things about different real world scenarios. So in this lesson in particular, for the videos anyways, we're going to be focusing on motion that we have talked about before, motion along a straight line, either left or right or up and down. And then in the worksheet for this video, there are more applications, but we're going to focus in terms of the notes really on these motion problems. So just to remind you, we have pointed this out in a previous lesson, but we've talked about the position function being s of t, whose derivative is velocity, and whose second derivative, or the derivative of velocity, is acceleration. So velocity is the instantaneous rate of change of position, and acceleration is the instantaneous rate of change of velocity. So when we analyze motion, which is what we're going to be doing a little bit more deeply in this lesson, we're going to start by looking at change in position. So a change in position is also called displacement. So that's what a delta S means, change in position. But it isn't necessarily equal to total distance traveled. So there's a couple of different diagrams here to sort of show this. So change in position, if you're looking at, like a position 1 and a position 2, will always be the later position minus the earlier position. Okay. So in this particular first example, if a particle or object starts at S1 and ends at S2, when you do this S2 minus S calculation, you're going to get a positive number because it's moved in the positive direction, and it'll just be the length of this line. So the change in position, the displacement, is equal to how far that object traveled. In the next picture, it's almost identical, but the particle or the object is now moving in the negative direction. So when you do S2 minus S1, you're going to get a negative number. It will tell you about the length of this line, but it will also be negative because it's moving in the negative direction. So the distance traveled will be equal to the absolute value of the change in position, because distance is always positive. But then for our third diagram, we have to throw all of that out of the window, because S1, S2, and S3, so we're talking about, in this case, an object that went right and then a little bit left. And if we do the displacement, which I've written here, it would be the final position, which is here, minus the original position. So it would just basically be this length right here, and it would be positive because it did move in the positive direction. But obviously the distance traveled is not going to be that. The distance traveled is going to be the length of this line plus the length of this line. So they're not even close. So I just want you to be aware, first and foremost, of the differences between displacement and distance traveled. So then we're going to just walk through the things that we need to analyze motion. That's what we're going to be doing, is analyzing motion. So first things first, we need to know when the particle is moving forward, or in the positive direction, backward, or in the negative direction, and when it is at rest. So which of the functions, position, velocity, or acceleration, is going to tell us about which direction a particle is moving? Velocity, exactly. So more specifically, can you fill in what do these 3 things mean? So when velocity is positive, what does that mean? The object is moving forward or in the positive direction, however you want to phrase that. Forward is shorter, right? When velocity is negative, then the object is moving backwards or in the negative direction. And when velocity is zero, the object is at rest. So anytime you're going to be analyzing motion, we're going to need to know these things pretty much right off the bat. And so a sign chart for the velocity function I can spell, is essential. You're just, anytime you're being asked about direction or of movement or when it turns, when it's at rest, you're going to need to make a sign chart for velocity so that you can see when is it moving forward, backward, then at rest. Okay. So then once we know that where a particle is stopped or turning around, we also want to know the position at those times. So that's the when, right? We will need to find the position. That's the where. Oh. Where is it when it is turning around? So you'll have some points from the above place where the velocity is zero, and you're going to want to plug those into the position to figure out where they are when those turns are happening, or those shifts in direction. Sorry about that. All right, and then lastly, we're going to be asking questions about speeding up and slowing down. So you might remember we had discussed this in a previous lesson. When we first started, we had one specific example, and we cannot tell about speeding up and slowing down directly from acceleration, because acceleration tells us how velocity is changing, but velocity itself can be positive or negative. So if velocity is negative and it's increasing, that means it's getting less negative. And so its speed, which is its absolute value of velocity, is going to be slowing. So couple little things we want to remember here. So speed, right, is the absolute value of velocity. So we need to look at when velocity, how the velocity is changing, which is the acceleration, and what sign the velocity itself is. You need to know both of those things. Okay. So I want you to take a minute to think about this. I mean, we can do let's do a couple together, and then I'm going to have you think about the other two. So let's look at the first one. If velocity is positive, so speed and velocity would be the same. Velocity is positive and acceleration is positive. Acceleration being positive means velocity is getting bigger. If a positive number is getting bigger, then its absolute value is also getting bigger. So then the particle is speeding up. Okay, so absolute value of velocity is increasing. So let's do one more. Let's do C. If velocity is negative and acceleration is negative, so I'm starting with a negative number, and acceleration being negative means velocity is getting smaller, is decreasing. So if I have a negative number that's decreasing, it's getting more negative. So what's happening to its absolute value? It's increasing. So that means that the particle is also speeding up. So see, it's possible to have a particle speeding up when there is a negative acceleration. The velocity has to also be negative. So press pause for a second and think through the other two the same way we just did, and see if you can decipher whether each of those scenarios is speeding up or slowing down. Okay, so I have that in both of these scenarios, the particle is going to be slowing down. Its speed, or the absolute value of velocity, is decreasing. So in B, I have a positive number that is decreasing. That's pretty straightforward. Then it's definitely, absolute value is definitely decreasing. And this last one, I have a negative number that is increasing. That means technically it's getting closer to 0, so its absolute value is getting smaller. So the good news is you do not have to memorize 4 different things, nor do you have to think through them every single time. If you've made sense of them, then I have a shortcut for a way for you to understand this or to remember it. If you look at the pattern of the 4 options that we had above, the particle is speeding up when velocity and acceleration have the same sign. So they're either both positive or they are both negative. And the particle is slowing down when velocity and acceleration have opposite signs. So one is positive and one is negative. So this is kind of the good way to remember it, but it is important, as I've said throughout this course, that you really have spent the time to understand why that's the case. Okay, so in case you do forget the shortcut, you could reason through the situation you're looking at.